Hello everyone, I'm Linan Huang from New York University. Today I'm going to present a topic on farsighted vulnerability mitigation of lateral movements using cognitive honeypots. Cyber-physical systems are facing new security challenge from advanced persistent threats, APTs, that differ a lot from the primitive attacks. For example, primitive attacks are opportunistic. They launch a lot of attacks and then pray that someone will be the victim. Whenever there is a vulnerability, they exploit it immediately. On the contrary, APT have specific targets such as a database to obtain confidential data or the actuator to cause physical damage. To reach the target at the final stage, APT can go through multiple stages such as reconnaissance, initial compromise, privilege escalation, and the lateral movements, which can last for years. These new attack features enable APTs to invalidate reactive techniques such as IPS and IDS. For example, APT can obtain the firewall setting during the reconnaissance stage to evade it. And also, stealthy APTs result in high error rates of IDS. Therefore, APTs can enter the system, stays in the system persistently, and remain undetected. Then the main security challenge for the defender is that he does not know when and where the initial compromise and the lateral movement happens. We use the following example of cyber-physical attack to illustrate the security challenge. The cyber network consists of host and client computers. Some of them are in the DMZ as they have to interact with the external network. Assets generally include hardware, software, and confidential information. For example, a programmable logic controller (PLC) can be a valuable asset because once it is compromised, attacker can control the industrial plants for the physical damage. An example is the Stuxnet virus. Due to the segregation of DMZ, which limit the attack surface, we assume that the attacker from the external network can only compromise the client or the host in the DMZ zone, but not in the internal cyber network. However, the attacker may still manage to compromise the assets by lateral movement, that is, to exploit the service links in the internal cyber network to move laterally to reach and compromise the assets. Here is an example timeline. At the initial state K0, the user clicks the phishing email and her client computer U1 is compromised. Then if he logs into the host computer H1 from U1 and enter the password, a hash is generated, and then it can be exploited by the attacker so that the attacker can access H1 in the future stages without the need to know the password. The hash value may have some time to live, and we assume that the attacker managed to compromise H1 and takes full control of it before the hash value expires. This is so called the patched hash attack. Since the attacker has compromised H1, he can share some Teams content on host H1, and once the user accesses it from, for example, U2, the attacker managed to control the user's client computer. And this is what happens in this two stage, and now the attacker has compromised H2 by this Teams share content attack. Suppose that a service session between H2 and H3 start at some time K0 plus 3. Then the attacker may successfully compromise the target node H3 from host H2 by remote service session hijacking. From this example, we see that the segregation only brings static security. So security at every static time does not guarantee security under a long period. To identify the attack path over time, we need to add these temporal links. Then we are able to see how the attackers managed to reach the assets from the initial intrusion over this long period. To formalize the idea of temporal links, we propose the following model of time-expanded network, which considers the user-host network at different stages as one network. The node side includes all the hosts and the clients in the network. The edge in the solid lines represent the service link at different stages, and the edge in dashed lines represent the temporal links. We assume the service link between two nodes happen randomly with the probability beta ij, and a node that does not involve in any service links is called idle at a stage. For example, this U2 at K0 is H3 at K0 plus 1. For the attack model, we assume that the initial intrusion happened only at a node in DMZ with some probability rho I. The attacker can exploit service link beta ij with success probability lambda ij to move laterally. There can be various techniques to achieve the compromise, such as the ones that we have already mentioned in example, but there can be many others. One way to counter lateral movement attack is to apply honeypots. The traditional honeypots are applied at fixed locations on machines in segregated areas. Therefore, it can be identified by the advanced attackers that these are honeypots, not the real service nodes. So here we consider a defense scheme of cognitive honeypots where the defender reconfigures idle nodes as honeypots and apply honey links from other node to it with probability gamma ij. Also, we change the location of honeypots at different stages so that it will make it hard for the attacker to distinguish honey links from the service links. This is what we call the level of stealthiness. So the main goal is to find the optimal honeypot policy gamma star to minimize long-term vulnerability, LTV, but we also consider other security trade-offs such as level of stealthiness. The probability of interference is that the honeypot should not interfere with the normal operation, and also there's a cost for changing the location of the honeypots. We refer to the LTV, long-term vulnerability, as the probability that attacker at the intrusion node I can compromise the asset J0 within $k stages. It means that attacker reaches node J0 before the final stage, and also it's not trapped by the honeypot. Since the attacker is stealthy, the stage of the initial compromise K0 is unknown. So this honeypot scheme aims to provide proactive and persistent protection. That is to say, we don't know when the initial intrusion happens. But once it happens, we want to reduce the probability that our asset will be compromised by the adversarial lateral movement. So we can compute this $k stage vulnerability by induction. This first term represents a successful immediate compromise of the assets. That means that the compromise is finished in just one stage. And if it's not successful, there is still chance because there are still k minus 1 stages left. And attacker may have already compromised some new nodes in the site V during his first move. Attackers may also try to compromise some nodes, but fails, and the site U consists of these nodes. For other nodes, there's no service link to compromise. So here we have to sum over all the combination of U and V, which is a lot of computation. Since the events of A can reach C and B can reach C are not independent, we approximate this term as a set of nodes by this union bound. Then we can have this upper and lower bound under a given policy gamma by the induction over stages from $k minus 1 to $k equal to 0. And at the boundary, this Jz is equal to Gz upper. So we omit the details on the computations, and we want to provide this following analysis of the LTV under two heuristic policy. The direct policy is to apply the honeypot deterministically from the initial intrusion in the DMZ to the honeypots. The indirect policy is random, but mistakenly exclude the nodes of initial intrusion. So these two policies are two extreme scenarios. The direct policy focuses on preventing the attack from entering the internal network, while the indirect policy put all effort in detecting and deterring attacks during the persistent lateral movement. He puts no effort in the first compromise. So there's some security questions that we asked ourselves. For example, how effective is the lateral movement for different lengths of duration time? What is the limits or the bounds of the vulnerability when the time window goes to infinity? And besides the honeypot's policy gamma, whether we can change the parameters such as lambda and the beta to help to deter attacks. So first, under the indirect policy, since there's no honey links from the initial intrusion node, we have zero probability of immediate capture, which lead to a non-decreasing vulnerability over stages. And then the target node will be compromised with probability 1 as the other case go to infinity. And here we define this probability of movement deterrence, POMD, which is the probability that attacks fails to move laterally from the initial intrusion I to any other nodes. To increase the R, we can either reduce the success rate lambda of the attack or reduce the frequency of the service link beta. However, these security measures will affect the usability. So the first one will increase the cost, and the second one will reduce the operational efficiency. With this R notation, we can compute the upper bound of the LTV long-term vulnerability by solving this first-order linear difference equation. This final term shows that the value increase exponentially concerning the duration delta k, and a decrease in a polynomial growth rate as the POMD is R increase. So we want to increase POMD by changing the parameter lambda and beta. But due to the usability trade-off as we have just shown, we cannot just let R equal to 1 for perfect security because that will make a system completely unusable. So here we aim to find the minimum POMD to mitigate LTV when the $K go to infinity. What we find is that the minimum is characterized by the threshold. And if this R is bigger than the threshold, then the limit of the upper bound is less than 1. If we further forbid the direct access of the asset from the initial intrusion in the DMZ zone, then the limit of the upper bound is 0, which means that we can achieve 0 vulnerability for infinite duration, and it means it's a long-term security for the assets. For the direct policy, which applies honey links from the initial intrusion to the honeypots, this is a better situation than the indirect policy, but we find that the security is still not perfect. We found that the indirect incomplete segregation will lead to a positive vulnerability residue, TVR, as this $K go to infinity. And also, if the value of LTV is less than T2, it will always increase as the number of stages increase. So let's conclude and review what we have done for this work. First, we're considering a cyber-physical attack scenario, which consists of initial intrusion from external cyber network, and the lateral movement in the internal cyber network, but finally for the damage in the physical network. Also, we have considered these two challenges of persistency and stealthiness. For the persistency, we found that the cascade of static security at all this time does not necessarily ensure dynamic security. Also, we cannot identify the entire attack path if we only focus on one stage or a short period of time. For the stealthiness, we just don't know when the attacker has entered our system, and we don't know where and when the lateral movement has happened. So that's the reason why we're considering time spent in network. As a comparison, the traditional attack graph model show the causal relationship from the preconditions to consequence. So it answers whether the asset will be compromised, whether the vulnerability will be used. From the graph viewpoint, it is a problem of connectivity. However, exploiting the same vulnerability at different times can lead to different outcomes, and some vulnerability can only be exploited within a given time window, as we show in the example. Therefore, we use this time-spent network to model the time-space relationship for an explicit attack path. So the question we ask is whether the asset will be compromised within a specific time, which is a reachability problem that can only be understand if we consider time explicitly. Finally, we analyze the long-term vulnerability and find out that first, the vulnerability is non-decreasing over the stages. The more stage an attacker can stay in the system, the more likely he can reach and compromise the vulnerable assets. And second, we identify a critical threshold of compromisability. That is, if the probability of movement deterrence is above this threshold, we can achieve zero vulnerability for the assets. Third, applying the honeypots may not achieve perfect security, and positive vulnerability residue it can exist as the stage goes to infinity. And that's all for today's talk. Thank you for your attention, and I'm glad to take questions.